Today's video is going to be mostly a reminder of things you've already learned. We're going to start by talking about the rate of change between 2 points. I'll give you a wordy definition and a mathy definition. The wordy definition, the rate of change between 2 points is the ratio, which remember means a fraction or quotient, of the change in y. Remember, y is our output, our dependent variable, divided by the change in x. As a formula, you'll have seen this before. We often call that rate of change m, the symbol for it. And if I were to have a line here, any 2 points on that line could be used to calculate the change in y and the change in x. So I'll use the 2 coordinates I have here, that one, and that one. I'll just label them to make it easier to use the numbers. That coordinate is -4, -4. This one is -1, -2. So if I wanted to measure the ratio of the change in y over the change in x, I need to figure out how far up that y value went and how far over the x value went. In some classes in Algebra 1, you might use the term rise over run as sort of a shorthand way of describing that. Well, the way we find how many units that is, of course, we can just count boxes in this case. But when it's a little bit harder to count, we always find distance by subtracting. So I'm going to subtract the second y value, the higher one, minus the first y value, and divide that by x2 minus x1. And you've definitely learned this before, whether you remember it or not. You called it the slope, which we can still keep calling it the slope. You'll see why I prefer the term rate of change coming up. And another term for it, which I'm guessing you actually haven't used before and probably won't really use much again until pre-calc or calculus. But sometimes that is also called the difference quotient. So maybe you'll remember hearing this term someday. The difference quotient is just another way of saying the rate of change between any 2 points. Now, every function, any 2 points on a function, you can calculate the rate of change. Most of the time, and for almost every function we're going to see all year long, the rate of change is not going to be the same for 2 points on a curve as it would be for another 2 points, except the one exception, which is the type of function you are already experts in, which is called a linear function. A linear function is a set of points whose rate of change is always the same. If we were to think about that on this picture, that would mean that if I were to keep drawing more and more coordinates, the rate of change between any 2 pairs would be the same. So if I went from here to the last one, that still is a ratio of 2/3. Now, if I do the subtraction, that's 4 and that's 6, which of course are different numbers from 2 and 3, but the ratio is the same, still 2/3. That makes a linear function. You probably know, and hopefully remember, that linear functions in Algebra 1, you usually use what's called slope-intercept form to write a linear function, and you write that as y equals mx plus b, where the x and the y are variables, meaning you can plug in an infinite number of different possible values for x and y. They just go in as a pair. So every x that you plug in would have a different y value. As opposed to the m and the b, which are what we call constants, which means for any one particular line or any one particular linear function, The m is going to be the same the whole time. That's the slope of the line. And the b is the y-intercept. Slope-intercept form is great. I don't use it much. I prefer what's called point-slope form, which some Algebra 1 classes go through it, some don't. So if it's brand new to you, that's totally fine. Point-slope form, it's just a different way of writing the same numbers. I'll give you what it looks like, and then I'll explain it. Y minus y1 equals m times x minus x1, which looks a little bit crazy, but it's not so bad. All that it means is if you were to try and write the equation of the line, so let's take this orange line up here that we're working on. All that you need to plug in are three little pieces. You need to plug in one coordinate on the line. That's x1, y1. Doesn't matter what coordinate you choose. I will use this one, -1, -2. Well, the -1 is the x1. The -2 is the y1. So I'm going to plug those numbers in there. And the m is, of course, the same m as up here. That's the slope. So those three numbers, those three constants need to be replaced by actual numbers. That's what makes it the equation of a line. The y and the x are variables. I can't replace anything in there. So y plus 2, notice how it became plus 2 because it's y minus -2. Those double negatives cancel out. That's why I write y plus 2 equals m times x minus x1, which was this -1 from up here. So again, the double negative will make that x plus 1, and that's the equation of a line in point-slope form. Notice how I did not get the y by itself, and that's totally fine. You don't have to. One other quick note, terms you've heard before, x-intercepts and y-intercepts. I want to make sure you think of them in a slightly more advanced way. Don't think of the y-intercept as, don't use the word y-axis in your explanation. The y-intercept is the output when the input is 0. In other words, it is f of 0. That is the y-intercept. And the x-intercept is the input whose output is 0. We don't have a nice fancy symbol like f of 0 for that. But any given linear function has an x-intercept and a y-intercept. If you ever want to find it, if you want to find the x-intercept, I'll put a note here to find the x-intercept. Set the y equal to 0, meaning plug in a 0 for the y, and solve for x. Which is an awful lot like what we would do to find the y-intercept. I've already told you that, though, because I called it f of 0, which we spoke about last class. F of 0 means finding the output when the input is 0. In other words, make x equal to 0 and find out what y is. Okay. We'll do one quick word problem, and that'll be it. At the start of a long road trip, Tyrell forgets to check his odometer. After driving for 4.5 hours, he sees that his odometer reads 54,225. After 6 hours, the odometer reads 54,360. Assuming that he drives at a constant speed, write an equation in point-slope form and slope-intercept form for the total mileage, that's our y, after x hours. And I cannot highlight enough, I'm going to literally highlight, but I can't do it enough, how important this and this, those few little words in our paragraph, are by far the most important part. Defining variables is the most important part of the process. A lot of times, they'll already tell you the definitions of the variables. Our input is the number of hours, our output is the total mileage. Sometimes you'll have to figure it out yourself, but it should always be the first thing you do. Your first thought needs to always be, what are my variables? What's the input? What's the output? In this course, we're almost never going to have more than two variables. What's the input? What's the output? Another important phrase in this particular example was this, that he drives at a constant speed. It is only because they tell us this. We would never have assumed this otherwise. And quite frankly, it doesn't make a whole lot of sense in the real world, but okay. This is how we know that we can use a linear function. If it did not tell us that he drove at a constant speed, we would not presume to guess that. But it did tell us that, so our first thought might be, all right, let's find the constant speed. Remember, the whole point of finding that rate of change is the change in the y values divided by the change in the x values. And they gave us the two y values and the two x values, and this is why it's so important to understand the variables. You have to be able to read total mileage as y, read this, and say, oh, that means that these two numbers are my y values. The coordinates that go together, 4.5 and 54,225, the 4.5 is my x, the 54,225 is the y. So it's a good idea to actually write that out as a coordinate, just so you don't get mixed up later on. That's one coordinate, and then the other coordinate is after 6 hours, he has driven 54,360. And so now we can find the rate of change by plugging in the numbers. We'll subtract the two y values. There's no correct order to doing it, but it certainly makes sense to me to try and keep my numbers positive. So I will take the bigger number and subtract the smaller number. And doing this math, it's 135 divided by 1.5. And dividing by 1.5 is not necessarily something that everyone does quickly in their heads. So one strategy that might make your life easier, and you might think I'm crazy for saying this is easier, but think in terms of fractions. Dividing by 3/2 I think is easier than dividing by 1.5, because you can turn dividing by 3/2 into multiplying by 2/3. You learned that back in middle school, that if you want to divide by a fraction, you multiply by its reciprocal. And a good strategy for dealing with fractions like this, always make your numbers smaller before bigger. Your life is a lot easier if everything stays smaller. So I'm going to do 135 divided by 3 first, which is 45. And only then am I going to multiply it by 2. So his rate of change was 90. And to figure out the units of measure, the rate of change, remember these were y values, these were x values, so the units of measure is the y value. Well, those were miles. 54,360, 54,225, those were miles. And the 6 and the 4.5, those were time in hours. So his speed was 90 miles per hour. Slow down, Tyrell. Well, the directions asked me to write an equation, and like I said before, all you need for the equation are those 3 pieces of information: an x value, a y value, and a slope. And with that, we can write the equation. Y minus the x value equals the slope. Sorry, I said y minus the x value, but I meant, and I wrote down, y minus the y value. The slope times x minus the x value of the point that we have. And there's your equation in point-slope form. If the directions would have ended here, I'd be done. They did ask me for slope-intercept form, so I'm just going to take an extra second and get that y by itself. I'm going to add the 54,360 to the other side, while also distributing the 90. And then I can combine those like terms, the negative 540 and the positive 54,360. And so that is the equation in slope-intercept form. this is the equation in point slope form. And now with that, I could now answer the question, any question about what is his odometer, say, or how many miles has he driven after any number of hours. I can plug in any number I want in for this x and figure out how many miles he's driven. Which doesn't sound all that impressive, but when you get to more complicated functions, like that's a big deal, to be able to write a complicated model as an expression where all you have to do is plug a number in, makes life a lot easier for a lot of complicated tasks.